Welcome to the topic, Trustworthy and Efficient Generative AI and Pre-trained Large Language Model for Next Generation Communications. My name is Dusit Niyato, the first presenter of this topic. Background: there will be strong industrial requirement for the 6G rollout and growth. It is projected that there will be IoT devices that occupy most of the radio resource in the 6G communication. There will be the paradigm shift from the cloud to the edge, where the network will be decentralized to achieve the low latency and better privacy. This is the concept of edge computing, where when the AI and machine learning model are implemented in the edge computing, this paradigm has become edge intelligence, and there are many applications, including autonomous driving, industrial automation, drone swarm, real-time healthcare. The edge general intelligence is the concept that introduced the advanced AI model to support various applications at the network edge. Currently, there are certain limitations for the cloud dependency because it causes high latency and single point of failure. The model, AI model and machine learning model are static, has a poor adaptability to the dynamic environment, and it has a limited scalability due to the constraint in the compute, memory, and energy resources. Therefore, we would like to introduce the paradigm that shift to the agentic AI, where we move from the passive IoT to proactive Internet of Agents. This agentic AI leverage perception, reasoning, action loop for true autonomy and real-time adaptation. To implement agentic AI concept, there will be four major components. The first one is model compression and compact model, because edge devices and edge server have a limited resources in terms of computing, communication, and energy. We are not able to deploy and run large AI model at the edge. Therefore, we need to reduce the size and customize and personalize the model based on the user and application requirement. Such a technique in the model compression include low rank adaptation, knowledge distillation, quantization, and pruning. Another key feature in the agentic AI is the energy efficient computing. Again, energy is very precious resource of the edge devices and edge server. We need to optimize not only the performance of the agentic AI, but also the energy efficiency. We need to look at the energy efficient design, adaptive inference mechanism of the AI model, and hardware aware optimization, how to utilize GPU, CPU, and memory based on the available flexible AI and machine learning model. Agentic AI will feature the connectivity and collaboration, where we need the robust inter-agent communication, decentralized task allocation, coordination, and incorporation of emergent communication and collective intelligence. The another feature is the knowledge representation and reasoning, where we need to ensure the accuracy and reduce or avoid hallucination of the large language model and agentic AI capability. Such a techniques include retrieval augmented generation on device knowledge base. For example, based on the knowledge graph, long-term memory, continual learning, casual and world model prediction. Motivation and objective of this topic. The key driver for this integration include critical requirement for the trustworthy and governable and explainable AI. This requires the mechanism to remove private, outdated, or harmful data from the trained model. We need the autonomous real-time intelligence in the dynamic and mission-critical environment, such as autonomous driving, low-altitude wireless network. There will be the demand to deploy the powerful large language model on the resource-constrained edge devices. This is to improve privacy and reduce the latency. By the end of this talk, the audience will be able to understand how to deploy the large language model on the edge network through the compact model or model compression strategy. We'll be able to learn how the generative AI can enable robust communication in uncertain low altitude communication environment via advanced channel estimation and secure beamforming. The audience will be able to explore the state-of-the-art large language model unlearning technique to ensure model trustworthiness and data governance without costly retraining. We'll be able to gain insight from real-world case study and experimental results in edge large language model deployment, robust beamforming, and certified unlearning. The structure of this talk includes the first topic about the trustworthy and efficient generative AI and pre-trained large language model for generate next generation communication. The second topic would be the generative AI enable wireless communication for robust low altitude wireless network. And another topic is toward edge large language model in next generation network. For the topic number one, trustworthy and efficient generative AI and pre-trained large language model. The challenges include we need to remove private, toxic, or outdated data from the trained large language model. This is technically complex and costly operation with a high risk of damaging the model overall performance. Currently, there is the lack of method to quantify and verifiable proof that data has been successfully removed or forgotten. The approaches and the robustness metrics will be explained. The topic number two, generative AI enable wireless communication for robust low altitude wireless network. Low altitude economy emerged as a hot research topic in many countries. The challenges here include low altitude wireless network facing high mobility, uncertain channel condition, and mission critical reliability requirement. In this topic, we apply the generative AI for the robust channel modeling, channel estimation, and beam alignment under dynamic low altitude environment. Topic number three, toward large language model in next generation network. Large language model has been used in many applications. However, running large language model at the edge of the network is constrained by the limited computing, memory, energy, and latency constraint. Therefore, we introduce the democratized generative AI through the compact model strategy such as distillation, pruning, quantization, mixture of expert technique. The goal of the tutorial in summary, we provide a comprehensive understanding of generative AI-driven communication. We offer the insight into the integration strategy of the trustworthy AI system. The focus is on the large language model unlearning. We present the practical technique and experimental validations for deploying compact large language model on the edge devices. More importantly, we highlight and emphasize the future research direction in terms of the scalable, robust, and governable AI for next generation network. We also explore opportunity for collaboration and future research direction together with the audience here. Thank you very much.
Hello everyone, my name is Yijing Lin from Beijing University of Post and Telecommunications. It's my great honor to make a presentation in IEEE VTC 2025 fall tutorial. And today our topic is about when LLM means unlearning, trustworthy and efficient model governance. Today we will introduce the background of LLM unlearning, our recent works, and the future directions. In recent years, we have witnessed the rapid rise of large language models. They represent a major paradigm, moving from narrow task-specific models to general-purpose systems. These models are trained on massive corpora of text and code, allowing them to capture word knowledge and linguistic patterns through self-supervised pre-training along with instruction tuning and alignment. The rise of the pre-trained large language models has been fueled by the convergence of data, compute, and algorithms. The digital transformation of our society have created unprecedented values of multilingual and multimodal data. At the same time, advanced in GPUs and distributed training frameworks have made it possible to train models with billions or even trillions of parameters. As a result, today we see a flourishing ecosystem, hundreds of LLMs and countless applications. As LLMs become increasingly powerful and pervasive, unlearning has emerged as a crucial capability for trustworthy model governance. First, there is a privacy concern. Training data often contain personal or sensitive information such as private conversations, identification records, or medical and financial data. Even if such data represent only a tiny fraction of the corpus, the model can still memorize and reconstruct it through membership inference attacks or specific prompts. This poses a serious risk to user privacy and data protection. Second, we face the problem of malicious, toxic, copyrighted, or poisoned data. The large language models can unintentionally learn from harmful, false, or copyright content that was injected into their training data. Without proper unlearning, these models might continue to generate misleading or malicious content long after the data should have been removed. Third, there is an issue of outdated knowledge. The world changes constantly. The fact it evolves, laws update, and context will be changed. If the model keeps generating answers based on outdated information, they can lead to poor decisions or even legal liability. Therefore, we need unlearning to remove specific data from well-trained large language models. Although unlearning sounds very simple, right? Removing specific data from a well-trained models. However, in practice, it's very challenging, especially for large language models. First, there are fundamental technical difficulties. Knowledge is stored in the parameters in a scattered and intervened manner, and a single local update can trigger global side effects, such as over-forgetting or some catastrophic forgetting, where the model loses general capability. Moreover, it's very hard to quantify what complete deletion rarely means, or to detect residual traces of the forgotten knowledge. And second, we face computational and other constraints. The intuitive way for unlearning is retraining from the scratch. We use the training corpora to train the large language models, which is prohibitive intensive computation intensive, both in cost and energy. In real systems, there may be multiple unlearning requests or concurrent deletions, amplifying the challenge. And for black box LLM service, where the parameters are not even accessible, direct intervention becomes nearly impossible. And finally, there are probability and trust issues. Even if we design an efficient method, how can we verify that the unlearning has truly taken effect? And more importantly, how can we provide auditable evidence to users or regulators that the data inference has been removed? These open questions define why LLM unlearning is not just an algorithmic problem, but a fundamental challenge for trustworthy model governance. Learning and unlearning are two sides of the same coin. In traditional training, we focus on acquiring as much knowledge as possible to minimize the loss and improve accuracy. But unlearning flips this objective. We aim to remove the influence of specific data while keeping the rest of the model intact. Technically, this means that instead of minimizing a single global loss, unlearning often involves balancing two opposing goals. The first is maximize the forget loss to erase target information. The second is minimize the retain loss to preserve useful knowledge. In other words, it's not about learning more, it's about learning to forget selectively. The process also differs in data usage. Learning uses the entire dataset to build capability, whereas unlearning works on a carefully defined forget retain partition, deciding what should be erased and what should be preserved. Finally, the way we evaluate changes as well. For learning, we care about accuracy and generalization. For unlearning, we measure forgetting completeness, utility functions, and even verifiability. Whether we can prove that the model has truly forgotten. So from learning to unlearning, the goal shift from the performance maximization to controlled. Now that we have seen how learning and unlearning differ, let's define what large language model unlearning actually means and what we hope to achieve through it. In simple terms, unlearning refers to the process of selectively removing the inference of specific data from a trained large language model without retraining the entire model from scratch. The goal of unlearning can be summarized in two key aspects. The first is effective forgetting. The unlearned model should behave as if the specific data to be removed was never part of its training corpus. The second is utility preservation. The unlearning process should minimize collateral damage, ensuring the model's core capabilities and knowledge on all other data remaining remain intact. We show the basic workflow of LLM learning, how we go from a pre-trained model to an unlearned model while ensuring that only specific knowledge is removed. We start with data partitioning. The dataset is divided into two parts. The forget set, which contains data that must be removed. For example, sensitive, copyright or harmful information, and the retain set, which represent the knowledge and skills that we still want to preserve. Next, we look at model state transmission. We begin with a fine-tuned model, which has already learned the knowledge to be forgotten. After unlearning, we obtain the unlearned model, where the target information has been erased, ideally without damaging its general abilities. Then comes the core unlearning process, an optimization that balances two opposing objectives. We maximize the forget loss to remove unwanted knowledge, usually through gradient ascent or equivalent penalization, and at the same time we minimize the retain loss to preserve useful knowledge. Finally, we perform evaluation. The first is forgetting quality, which means the model should perform poorly on the forget set. And the second is utility preservation, which means it should still perform well on the retain set and general knowledge. Even though the workflow of unlearning seems well defined, it remains some challenges. We can summarize these challenges into three major aspects: credibility, reliability, and practicality. For the credibility, unlearning is often unquantifiable and unverifiable. It's very difficult to measure how much influence a particular dataset had on the model or to what degree that influence has been removed. Moreover, we currently lack trustworthy third-party auditing mechanism to verify that unlearning has actually occurred. Second, reliability. Most heuristic unlearning methods produce randomized effects. They may work on one dataset but fail on other, leading to inconsistent or incomplete forgetting. Over multiple iterations, this small deviation can accumulate, causing model drift and performance instability. Third, even if an algorithm works on theory, it's very difficult to get the model to have access to the model parameters or logics. We can only use closed box APIs to access the large language models. Now we will introduce some our recent works. The first one is certified unlearning with drift-bound guarantees for large language models. It's under review. Existing unlearning approaches can be grouped into three main categories. First, for retraining, later we retraining the large language models from scratch, but it's very impossible, both computationally and economically. And second, current unlearning method use heuristic strategies to determine when we should stop the unlearning process, to determine the unlearning epochs. But such method often stopped may be too early before the model truly forgot or continue too long, causing overfitting, right? And there are some machine learning based methods to determine when we should stop the process. However, this method like differential privacy or some other method cannot be applicable to large language models. Therefore, it's necessary to develop verifiable early stopping mechanisms that determine when the forgetting process is sufficient to achieve compliance with minimal computational cost. We propose a certified LoRa unlearning method that treats each deletion as consuming a total variation budget and enforce it via Frobenius norm projections. There are 3 contributions. We are the first to propose a theoretical stopping rule for large language model certified unlearning, deriving a closed form mapping from the Frobenius norm of model update to a tight TV bound on model drift. We introduce Graham-Schmidt orthogonalization to ensure an additive and composable TV upper bound of model drift. And we evaluate our framework on E6B with archive and GitHub subset to validate the effectiveness of our proposed method. Our framework established a 3-stage certified LoRa unlearning pipeline that guarantees bounded distributional drift through TV constraint update. It includes 3 stages. The first is trust region and ascent. Under the present TV budget, we calculate the radius of the trust region according to model parameters. Then we perform gradient ascent update on LoRa depths. If the update reaches or exceeds our trust region, then we stop. The second stage is projection and certification. If the final updated value is larger than trust region, then we project it onto a sphere with a radius of trust region, and then we record the actual TV budget consumed. The above 2 stages are designed for the single unlearning request. For continual unlearning request, we use orthogonal integrations. Each unlearning request will occupy and directions to reduce the interfere between those requests. We use Graham-Schmidt method to orthogonalize the current update with respect to the historical updates. Then we ensure that the TV budget can be accumulated and does not interfere with each other. These are the major results of our proposed method. We evaluate our framework on E6B with large language models with archive and GitHub subset. Our representative method compared with some to the unconstrained update and achieves a forget PPL increase of 0.84 and reduce the return PPL. And we can also improve the downstream the accuracy of the downstream task and maintain a cumulative TV distance strictly below the bound. The second work called CBD, API-only large language models black box unlearning through controlled behavioral divergence. There are two categories of existing method to solve the efficiency of large language models on learning. The continual training-based method employed by directional gradient optimization strategy, performing gradient ascent or its variant on the forget. And the second one is the auxiliary model-based method, which introduce additional model to calibrate the log probabilities of target models. However, those two methods have some drawbacks. The first one, it requires direct model access, causing high cost and long unlearning cycles. The second one require the model logics, which are not exposed in commercial LLM APIs. In summary, the existing two methods all requiring access to the large language models using model parameters or model logics, which are not applicable for the API-only large language models. To solve the above issues, we propose a novel API-only large language models learning method that operates in closed box scenarios without requiring access to multiple parameters, gradients, or internal probability distributions, making it practical for commercial large language model deployment. It includes three contributions. The first one is this framework enables selective data learning through controlled behavioral divergence between the two auxiliary models, ensuring that the forget-related data is dynamically routed while maintaining the overall model performance. The second one is we introduce a gradient orthogonal projection method to construct the auxiliary models, which ensure that the behavioral divergence occurs mainly on the forget set. The third one, we propose a token-aware-weighted cross-entropy mechanism that assigns higher importance to tokens likely to reveal forget-relatedness, enabling precise query routing for unlearning. And the core idea is to construct two auxiliary models, where one maintains the original state unchanged and the other undergoes preference optimization training using forget set. This creates controlled behavioral divergence that serve as a representation of query forget relatedness for dynamic model routing. Our proposed method includes two parts. Part A, the return set basis, is first extracted from the activation representation matrix of the return set using SVD. Then gradient updates are applied in directions orthogonal to this basis, ensuring that only the forget set is influenced while preserving the performance of the return set. It solves the challenges in requiring access to the original model, including model parameters or logics. Part B, based on the constructed dual auxiliary models, the system applies token-level forget-relatedness discrimination using weighted cross-entropy to route forget-related queries to the auxiliary models, while normal queries are directed to the target large language models. It solves the challenges of determining the relative importance of tokens, as not all tokens contribute equally. Now we show our major results. For effective unlearning with 5% forgotten data, the response similarity on the forget set can is 31 and the token probability is 23. The unlearning performance outperforms existing method approaching the retrained model. And for the computational efficiency, our proposed method can use less model parameters and less GPU memories compared to full retraining. The third work is quantifying and certifying unlearning for large language models. Current existing unlearning methods rely on gradient parameter modification or logic perturbation. However, they cannot quantify and verify unlearning method without full training. To solve this problem, we considered how to balance computational efficiency, data value transparency, and verifiable reliability in large language model forgetting. Our contribution including 3 parts. The first one is quantification. We designed a runtime sharply value mechanisms with a first-order approximation to efficiently estimate forgotten data contributions. The second one is verification. We propose a proof of unlearning mechanism that generates auditable artifacts and verifies removal correctness via trajectory correlation. And we evaluate our framework's effectiveness on benchmark dataset for both data contribution quantification and unlearning certifications. The overall workflow of the proposed framework including 2 parts. The first part is runtime sharply based quantification. This part introduces a runtime sharply value mechanism with a loss-based utility function. We use a first-order approximation to efficiently quantify unlearned data contributions without retraining. As we all know, the sharply value is notorious on the computational cost. And to solve the first part, runtime sharply based quantification can quantify how much each unlearned sample contributes to the model behavior. The second part is proof of unlearning verification. This part records and sample roller adapter updates and applies correlation analysis on replied trajectories, generating transparent, auditable proofs that certify correct data removal. It can verify whether unlearning has truly occurred, especially for large language models. Specifically, runtime sharply value for unlearning should quantify unlearned data inference with efficient first-order approximation. First, we will define a utility function. We use loss-based utility to balance retention and forgetting objectives. We measure loss variation on retain and forgot set between consecutive updates and enable per-step evaluation of marginal contribution for each data subset. Then we design a first-order approximation strategy to avoid expositional cost of exact Shapley estimation. The first-order Taylor approximation is utilized to reduce the computational cost, and we utilize gradient information to estimate marginal utilities, and we eliminate the need for retraining or second-order computations. For the proof of unlearning method, it includes 2 parts. The first part is POU creation. We first freeze backbone and update all roller adapters. And for each unlearning step, we will record adapter, state, batch, and hyperparameters. Then we aggregate those parameters into transcript as a compact proof log. Finally, we provide a verifiable record linking parameters update to forgotten data. To verify the record, the verifier samples few steps and replaces corresponding update. The verifier compares parameter change distance with records once, and it computes Pearson correlation between replayed and declared trajectories. Finally, we can ensure that the lightweight and scalable verification of unlearning authenticity. These are major results of our work. For every method and both datasets, our Pearson distance curves increase almost linearly with the checkpoint interval, and our proposed method can shift AUC by almost 0.01 for every base time, confirming that POU preserve the forget effect without altering membership privacy. Then we introduce the it includes three-part privacy preserving data-free unlearning, multi-model data unlearning, and unlearning for federated system. Even we use the large language models unlearning, it can still pose privacy leakage risks. And the current methods focus on texture data. We should consider multimodal data unlearning in the future. And as the large language models are widely used in federated systems, we should consider the unlearning for federated systems. That's all. Thank you for your listening.
So hello everyone. Today I will be talking about generative AI-enabled robust low-altitude wireless network. I'm the speaker, Jiachen Wang from Nanyang Technological University. So we have two papers available online. So if you're interested in this topic, please feel free to scan the QR to get access. Before we talk about low-altitude wireless network, we have to introduce the low-altitude economy. So which refers to the economic activity that takes place within the airspace below 1,000 meters and potentially extending to 3,000 meters, depending on the specific requirements. So within this kind of low-altitude airspace, we can have several applications here, such like low-altitude logistic, delivery, inspections, and also the medical supply. So according to the CAA of China, the value of Chinese low-altitude economy surpassed 500 billion Chinese yuan in 2023 and is projected to reach 3.5 trillion Chinese yuan by 2035. So besides China, we also have other countries trying to explore this kind of low-altitude airspace. So modern intelligence forecast that the urban air mobility market will grow to 4.04 billion US dollar by 2029 in US. So we can see there's a huge market in here, not only in China, but all parts of the world. So come back to the low-altitude wireless network, which we consider can be used to support many economic activities within the low-altitude airspace. So this kind of network have many functions, of course, and we list the three main of them. The first is low-altitude computing, so which means the UAV can be used as area nodes to provide the computing support for many applications like air taxi. And besides that, we have low-altitude communications. So this means that the UAVs flying in the sky have to communicate with each other, and even sometimes they have to communicate with their base station and even the satellite. So the third one is longitude sensing. So the signal transmitting among these UAVs form a huge network which can be used to sensing the target. The target means the UAVs and even the target vehicles on the ground and the people on the ground. So again, of course, we have many more functions besides these two, and here we just list the three of them. So for the low altitude wireless network, what matters most? So the answer is the robust. Here we list the three main reasons. The first is the high stake. So laws are highly dynamic and often used in mission critical operations such as emergency response and critical deliveries, like we mentioned, the medical supply. So failures or downtimes can have serious consequences, making the reliability paramount. The second one is uncertainty. So unlike the regular on the ground, they can stop whenever or even wherever they want. The jaws in the sky face a lot of unpredictable elements like wind blow, obstacles, and signal differences. So robust means here the network can maintain the quality of service despite these uncertainties. So last one is security. So many lost use cases involve the sensitive tasks. So a small breach or attack can degrade performance or even cause very serious accident. So the robust here means design ensures the safety and the security. So what kind of QAS matrix can be used to describe the robustness of the low altitude wireless network? So here we generally classify them into four categories. The first one is system accuracy, the second one is communication rate, the third one is a computation resource, and the last one is control stability. So besides them, in fact, we have many more other QAS can be used to describe the robustness. We just list four kinds of them here. So for example, the sensing accuracy, we have a matrix like time of arrival and channel state information, and even the received signal strength can be used to describe the sensing accuracy. Besides that, we have a communication rate, which focuses on the data delivery performance with the matrix like outage probability, bit error rate, and the spectrum efficiency. So robust here means keeping the outrage and error low while maintaining the three outputs under varying channel conditions. Besides that, we have a computation resource and control stability. So here, for example, the control stability influence the speed, trajectory, and the state of a device, which we can consider as UAV, significantly impacting the channel quality signal. So the control stability can be achieved by optimizing the trajectory tracking accuracy, disturbance rejections, and the stability margin index. So now we have the motivations, we have the scenarios, and as well as the matrix can be used to describe the robustness. So next question is what kind of method we can use? So the answer is uncertain optimization. Here we list three kinds of uncertain optimizations. The first one is stochastic optimization, so which accounts for uncertainty by optimizing the expected performance across multiple conditions and scenarios. Then the second one is chance constraint optimization, so which ensures that the low altitude wireless networks meet predefined requirement with a probabilistic guarantee, so effectively managing tolerance to errors with acceptable limits. So last one is robust optimization, so which tries to optimize the worst case performance under the uncertain conditions. So here we list one more deterministic optimization at the top. So this one is considered as the baseline. It tries to optimize the performance indicators under the fixed conditions, improving the efficiency with a predefined environment. So we have this kind of way to optimize. Then the next question is what kind of method can be used to solve this kind of optimization problem. So here we focus on the generative AI. So unlike the discriminative AI, which trying to nurse decision boundaries between the classes or the optimal actions for given conditions. So generative AI tries to nurse the data distribution, the insight patterns, and after that, it leverages the nerd insight patterns to generate a new result based on the newly input conditions, which we can considered as a new environment or the new channel environment or new channel conditions. So more formally, generative AI refers to a class of artificial intelligence models capable of generating new content such as text, image, audio, and video based on the training data. So this model have revolutionized various industry by enabling machines to create human-like output, offering powerful tools for creativity, productivity, and automation. So here we list some of the representative apps. Like first one, we can say the ChatGPT, which we are very familiar with, can be used to generate the text and sometimes the code also. We have a Chinese version called DeepSeek. Besides that, we have Stable Diffusion, which is famous of generating high quality images. Last one, we have Sora. This is also released by the OpenAI, which can be used to generate the video based on the input prompt. So these are some representative um, generative AI-based applications. Besides that, we have even more. So based on the basic principle of generative AI, we can see in low-altitude wireless network, GenAI holds this kind of three key capabilities. The first one is handling the dynamics. So the generative AI proved highly effective for complex area network, offering precise monitoring and control capabilities even at a very high UAV speed. So besides that, so another key capability is latent distribution mapping. So a key strength of generative AI is mapping the latent distribution to the physical parameters. So this provides deeper insight into how the different factors interact, enabling the system to manage multiple parameters together. So the last one is handle the correlations. So traditional method often treat issues separately, whereas the generative AI handles them holistically. So it captures the correlated effects and addressing the combinations of challenges. So in low-altitude wireless network, generative AI have this kind of three representative applications here. The first one is the channel modeling. So traditionally, we have to use like ray tracing to compute the propagation path parameters, thereby to achieve the channel modeling. So here we can use these parameters to train the generative AI. Then when the new condition comes in, we can use a generative AI to generate the propagation path parameters directly, thereby achieving the channel modeling, which is more fast. Besides that, we have a channel estimation. So generative AI can be used to reduce noise of signal, including the Doppler effect and the multipath distortion. So it also estimates accurately the channel information in various operating environments, including the hash rate. So the last one is beam alignment. So generative AI handles temporally correlated observations, supporting a deeper analysis of the implicit relationships. So it can also optimize the beamforming and resource allocation effectively, increasing the spectral efficiency and link reliability. And besides these applications, there are some also limitations of generative AI we need to discuss. So from the security perspective, we list three kinds of limitations here. The first one is high complexity. So as we all know, generative AI models are highly complex due to their sophisticated algorithms, especially the training process and the long inference time. So in rapid changing environments, these models may have difficulty detecting and defending against the cyber threats when the resources are limited. The second one is low adaptability. So the reliance on the predefined dataset makes generative AI models inherently inflexible, hinder the effectiveness in diverse and unfamiliar situations. As the model grows, retraining it from scratch becomes more difficult, reducing its ability to adapt to unexpected events. So this one leads to the last part of the limitation. It is a limited detection performance. So generative AI concentrate on a narrow range of security threats, so leading to a limited performance when applied to new and complex real-world scenarios. it is difficult for them to accurately detect a threat that's derived from the training data. So to handle these limitations, we have to introduce the mixture of expert structure. So the MOE structure is based on the divide and conquer principle. It assigns tasks to the specific submodels, or we call the expert, for tailored approach to managing complex data. So by leveraging the unique strengths and expertise of multiple specialized submodels, MOE aims for high accuracy and efficiency in the computational problem solving. Generally, MOE has three key components. The first one is a gating mechanism. So this one, it evaluates the input and select the most relevant expert. So effectively routing the data to the most relevant expert models to handle. So the second part is expert models. So each expert model is specialized in different tasks, handling complex patterns more effectively. So last one is combining the output. So here the gating network again collected output of each expert and to form the final result and the feedback to the user. So here is the general description about the MOE. So here we provide two conceptual examples of MOE structure. The first one is focused on the input data. So we can have a different expert processing different kinds of data. So then we form the final result. The second one is focused on the output. So this kind of example means we have a different expert processing different kinds of data and output different kinds of data like temperature data and audio data and video data. This kind of data are combined finally together to form the final result. So we incorporate MOE into generative AI models. We have again get a lot of benefits, and we list three main of them. The first one is enhanced detections. So MOE enable generative AI models effectively address the challenge of learning complex distributions from hybrid attacks, including diverse spoofing and jamming types. By assigning each expert to specific attack patterns, the architecture enhances modeling precision while maintaining the relative simplicity in individual submodels. Second one is resource efficiency. So in the inference phase, standard generative AI models require full network activation, so limiting their deployment on resource-constrained edge devices. So the MOE architecture guided by a gating mechanism activates only the most relevant expert for a given task, significantly reducing the computing load while enabling efficient and real-time response to the cyber threat. The third one is adapt learning. So adapt to new threats such as attacks, jamming attacks from unseen sources, typically requiring training the entire generative AI model. So now we have MOE here. It mitigate this by updating only the key parameters brought by the scaling mechanism, reducing the training overhead and enhancing the model's adaptability to the evolving attack patterns. Based on the previous discussion about the background, the matrix, and the generative AI and the MOE, here we propose our framework. It is called the MOE Transformer Actor Network for diffusion-based optimization. It contains three components. The first one is diffusion policy. So we can see here is we describe some denoising process and the most important one, the actor network. The actor network includes the following two components. The first one is mixture of expert, and the second one is attention mechanism. The first part is diffusion policy, which is a policy generation method using a denoising diffusion model. It models action sequences as distribution and generates them via the iterative environment, similar to the image generation in stable diffusion. Instead of predicting the next action directly, diffusion policy generates the action via the denoising process, which is more stable. So as the figure shows, the robot's arm can generate the orders to move the T letter back to its space. So besides the diffusion policy, we have MOE and the transformer, which is basically the attention mechanism. So the MOE has the following three advantages. The first one is efficient use of large parameter space. The second one is better generation, because we have a lot of experts and each of them are good at the specific area. So if we combine a lot of experts, we can handle a lot of tasks here. So the third one is ideal for multitasks. So for the attention mechanism, we have the three following advantages. The first one is selectively attend to the relevant parts of the input, so it does not need to activate the full network. The second one is it can capture long-range dependencies regardless of the distance. The third one is it can enable efficient training via the parallel computation. Here we provide our case study here. The generative AI enabled the robust beamforming for the secure communication in low-altitude wireless network. Here we consider three kinds of uncertainties here. The first one is position uncertainty. The second one is channel uncertainty, and the last one is angle of arrival uncertainty. In fact, the third one and the first one is quite overlapped. So when you deploy or consider your own models, you can select one matrix from the communication, another from sensing, and the last one from the control, and etc. So to make the model more robust and consider more perspective. So we input this kind of uncertainties into the trained generative AI model, and the model will feed back the beamforming matrix to maximize the achievable secure rate in this kind of low altitude airspace. Here's a general description about our case study. So here we give a more detailed description about our case study. To ensure the reliable communication while mitigating the eavesdropping risks, we accomplish secure beamforming by solving an optimization problem. Our object is to maximize achievable security rate by optimizing the beamformer for both computational signal and artificial noise, accounting for various sources of uncertainty. To restrict the eavesdropper's ability, we impose a constraint that limits the capacity of the eavesdropping channel to remain below a specific threshold. So we consider three kinds of optimization we mentioned previously also. The first one is stochastic optimization. This one aims to maximize the mathematical expectation (ASR) for given beamforming actions under uncertainties. We incorporate the eavesdropping channel capacity as a peanut term to enforce constraints. The second one is chance constraint optimization, which tries to maximize ASR while ensuring the constraint satisfaction with uncertainty probability. When the constraint satisfaction probability is greater than 8, we only calculate the reward brought by ASR to maximize ASR from the probability perspective. The last one is the robust optimization, which focuses on the guarantee the worst case performance under uncertainty. For given beamforming actions, we use the Monte Carlo method to approximate the worst case with the lowest achievable reward. Then we maximize this lower bound to enhance the robustness of the generated beamforming. Here we provide our simulation result for the constructed problems. We provide the result of all three kinds of optimization and also the inference reward shown in the figure D. So from the result, we can see first, the proposed MOE transformer framework improves the final reward by around 13% in stochastic optimization and around 15.79% in robust optimization, while achieving performance comparable to baseline under the chance constraint settings. The second one is generative AI without the MOE transfer architectures often fails to learn the effective policies in several scenarios, whereas the proposed framework consistently learns secure beamforming strategies faster and more effectively. So we can see from the curves. The third one is compared to the long generative AI. generative AI baselines. The proposed method delivers superior results across all optimization settings. For example, the GenNN performs poorly under the robust optimization, and the pure transformer underperforms in the stochastic optimization. So last, the proposed generative AI model achieves the highest minimum reward with the lowest variance of around 70 under the robust optimization settings. The less variance results in a more dependable and robust safety margins against adverse conditions. So last one, we provide some future directions for you to explore. The first one is the adaptive for dynamic environments. So as we all know, laws facing rapidly changing conditions. So to ensure effective deployment, we may consider apply online learning and real-time model adaptations. So besides that, use the context-aware optimization to track missions and environment changes is also critical. The second part is anomaly detection and recovery. Here we consider the multimodal anomaly detection, which means the data collected by different sensors like cameras and communication base stations, and even sometimes the radar can be used for the anomaly detection. So besides that, the real-time, once we detect the anomaly, we can conduct the real-time recovery strategy. So here we must consider the rerouting and the resource allocation. So the last one is energy-aware generative AI optimization. So this part focuses on the generative AI model itself because the UAV has limited power. So the power constraints requires the smarter design. So this point focus on the lightweight architecture of generative AI and also the energy efficient inference and collaborative edge processing to prolong the network life. So here are three main points of the future direction for you to explore. So that's all about my topic today. And besides that, we have one couple paper here. So we have a TVT special issue called the Low Altitude Wireless Network. So we have listed some scope here, which is quite general, including the architecture design, cross-layer optimization, ISAC, and some security issues, and etc. So the deadline, the submission deadline is February 2026. So we still have several months to prepare, and the initial decision date should be around April. So hope we can collect more high quality papers here. Thank you so much for your listening, and if you have any questions, please feel free to drop me an email, and I will reply you once I saw the email. Thank you very much.
Good morning, everyone. I'm Rui Zhang from Nanyang Technological University. Today I will discuss edge large language models, why we need them, and how to make them practical under strict resource and energy budget, and what a democratized edge large language models ecosystems looks like in real deployments. Edge large language models are large language models executed directed on edge devices or near edge nodes for local inference and processing. Compared with cloud online pipelines, they often offer some lower latency, better pricing, and more resilient operation in constrained or intermittently connected environments. In this talk, edge spans phones, variables, on-premise gateways, and macro-edge servers. The high-level aspects we will keep returning to are model efficiency, system compilation, and service experience under realistic constraints. And edge large language models come for massive compute and memory demands and strict energy budgets. Training, adopting, and even running inference for large language models agents can quickly exceed device capabilities, especially when we require consistent latency and thermal safety. This tension motivates a design agenda that reduces model and runtime footprint while preserving utility. The response emerging in the committee and in our work we can call democratized large language models, which couples compact modeling with system-level optimization and a practical toolchain. Okay, by democratized large language model, we mean an approach that highlights openness and sharing, equal access, and low barrier operation across heterogeneous devices. Correspondingly, it prioritizes localized processing and privacy preservation, allows personalized customization of models, and maintains cross-platform compatibility by portable runtimes. The pivotal idea is a compatibility across diverse sectors without exclusive hardware or some proprietary stacks. Functionally, democratized large language models must expose clear capabilities, predictable performance, developments, and some privacy boundaries. Here is an overview of the democratized e-learning models, and now we summarize some compact strategy like fine-tuning, knowledge distillation, MOE, model pruning, and quantization. And we also have some metrics such as hallucination rate, resource consumption, generalization accuracy, and accessibility. And we also summarize a table to show the different key strategies in terms of the advantages, disadvantages, and model size reduction, and some relationship with the metrics and the KPI. For examples, like fine-tuning, we can say the advantages are reduce training time and improve domain adaptability, but the disadvantages are the considerable training cost and the risk of the overfitting to small data sets. And we can also see the relationship with the metrics and the KPI. The generation accuracy will become higher and more accurate, but the hallucination rate will be descending. Accessibility is also can be increasing because of the fine-tuning can improve the domain and adaptability, and the resource consumption will be decreased. And this is some representative works in recent 2 years, and we can see from the three diagram we can find that in the past 2 years many research works have emerged to improve and optimize large generative AI models such as large language models, which will further promote the realization of the democratized generative AI large language models in the next generation mobile edge networks. Here is a comparison table of the key compact model strategies. And we can see the different strategies like we just mentioned, fine-tuning, model pruning, knowledge distillation, quantization, and MOE. And we will show different kinds of the training methods, applicable network types, user demand, generative AI applications, and some application examples. For example, like quantization. Quantization uses large memory and throughput gains, but many increase hallucination and degrade generalization if overly aggressive. And also for pruning removes redundant weights or heads. Structured pruning benefits runtime more than unstructured variance. Distillation aligns a compact student with a teacher on token or sequence level objectives, often the best quality preserving path. And something like the LoRa support some efficient specialization and personalization. And in practice, hybrid some reception from distillation to the low bit quantization and then to the device aware compilation are most robust. Here we show one case study about the real deployment process of the democratic EG large language models. And here is our workflow. So step 1 is a model selection and fine-tuning for target tasks. Step 2 is a model compilation by using a tensor VM or TVM like Stack or MLC large language models to generate device optimized artifacts. The step 3 is for deployment and evaluation by using Android Studio or Edge runtimes, measuring latency, energy efficiency, generalization accuracy, hallucination rate, and resource consumption. And the last step is the offloading strategy. It is for to a near each node for tail cases. The goal is to repeatable build artifacts and instrumentation that expose real-world trade-offs. And here is our case studies result, and we can see we use the 4 metrics we just mentioned and compared with different kinds of the compact model strategies. And we can see the different models or different strategy will have a different effects and effectiveness of the in terms of different metrics. And we can see this figure, the here quantization can have a better resource efficiency and more better accessibility. And we can also have the trade-off, increase the hallucination rates, but reduce the generalization. So after that, we are wondering whether we can do some offloading strategy, like if we have some complex inference task, we can do it on the online. But if we have some simple inference tasks, we can do it maybe do the locally or offline. So we consider use the offloading model. That means we did this simulation results. That means we have 3 different strategies. The first one is all of the tasks are considered in the mobile edge devices. And the second, the green line to show all of the tasks are doing on the edge server. And the last one, the blue line, are showing that different tasks doing on the local, it means the mobile edge devices, and the rest parts should be doing on the server. And then we can see after the offloading, we can see the hallucination rate is better than the mobile edge that is doing on the mobile edge, but the accuracy rate maybe is lower than the generation accuracy. So that means they should have a trade-off. That means use powerful edge models for complex tasks, and it also can reduce some hallucination, improve the generalization. And the result also can show it should be performance a pure local execution. And here is another extended work. In this work, we study covered prompt transmission, where IDs compresses and encrypts a user prompt with a small large language models and transmits to Bob will remain undetected by VD. We propose a PCAE, a prompt compression and encryption framework using surprise or guided token section at the edge and a group-based PPO. That means GPPO method that jointly optimizes compression ratio and transmit power. The objective is low latency delivery with prompt fidelity at Bob and correctness against VD. And here is our problem formulation. We formulate latency minimization under constraints on reliable reception at Bob and correctness with VD. PCAE maps an original prompt to a compressed encrypted sequence. Semantic fidelity is evaluated with bird score. And over the various link, we analyze achievable rate and total transmission time at Bob. VD performs binary hypothesis testing, we control his false alarm detection probabilities by using power and compression decisions. This yields a constraint IO problem for GPPO. And after that, for our proposed PCAE framework, we use offset-based token perturbation plus permutation to mask token positions. For compression, compute token separated from small language models, logics, and select informative tokens, keeping semantic sufficiency while shrinking the sequence. A simple example illustrates how a phrase's surface form is obfuscated yet remains reconstructible at Bob. PCE after that, PCE decoupled edge feasible scoring with lightweight cryptic transformations. Now to the end-to-end PCE pipeline and how its behavior under different model sizes. And here is some simulation result. We can see the large models response fidelity under different model size and compression ratio using PCE, and we can see different parameters of learning model have different effects, and but if the parameters is large, so the performance will be better. And another one is to show the compression PCE and SOTA baselines under a server equipped with NVIDIA 800 GPU, and we can see our method is much better than the baseline in terms of the computation time. And here is our proposed GPPO approach. That means for this one, we use generative advantage estimation. After that, we normalize advantage maximum advantage within a group, and we choose the maximum one, and then to do the next step. And here is some simulation about our GPPO, and we can see different metrics like accumulated reward, transmission latency, large model response fidelity, and detection error probability. And we can show our GPPO is the best in terms of these metrics and compare with the different baselines. And here is another case studies about the edge learning models assisted optimization. For this one, the system and the workflow, the framework we can call Stella. Stella targets downlink satellite networks with RSMA, aiming to maximize the sum rate by jointly optimizing beamforming and the common rate allocation under power constraints. The pipelines uses a large models assisted evaluation loop. That means large models guided proposal, domain-specific evaluation, and iterative section to accelerate search over a difficult non-convex space. This blends expert priorities with generative search to reach high-quality configurations faster. So let's look at its convergence behavior and rate gains, and we can show the convergence behavior is faster than the traditional PPO and IR method. Even our effect is close to the benchmark one, the upper bound one, yeah. So the next picture is about a triple rate compression under different method. We can also see if using our Stella, it should be much better. In terms of the triple rate, it's the best compared with the vanilla PPO and the random baseline. So yeah, here is the conclusion. That means the EGI implementation challenges, and we have the different case studies to show the and why and how we can to address the challenges, and we also show the two different works. And let me to do a promotion, because now I'm a TSE assistant, the ESA assistant. that means the managing editor. So if you have a paper related to this topic, please feel free to submit your paper to TNCE. TNCE is always welcome to these papers. Yeah. And here is our one of our special issue, and this special issue is also related to large language models and agent AI. The topic is agent AI for communication and networking with embodied intelligence. So the manuscript submission time is next year January. So please feel free to submit your paper. And that is another one is the IEEE transaction on artificial intelligence. So this special issues topic is sustainable large AI models for intelligence. So the manuscript submission time should be this December. So if you have related paper, please feel free to submit. Okay, that's my talk and my tutorial part. So thank you so much for your listening. If you have any question, please feel free to let me know by email. Okay, bye bye.